Restart. Hello everyone, welcome to MetaGate. And today we will be basically talking about non-ferrous extractive metallurgy. So this is going to be a one shot. So we will cover mostly all the important topics that are there in the non-ferrous. Now before this, we have already covered our substantial portion of mineral beneficiation techniques, and iron making and steel making is also covered in the one shot. So in the mineral beneficiation technique, we have basically covered some of the parts because it comes under mineral beneficiation only. Some of the parts means like we have covered froth flotation method, which can also be studied under this section. But I think we should first and foremost we should start with pyrometallurgy. So first, just by this word, pyrometallurgy, what does it mean? We need to understand. So pyro means actually this pyro, this word, P-Y-R-O, pyro, it means fire. Okay, just if I write this word pyro, it means fire. And metallurgy is the process of extraction of the metals, as you all know. Now, so if I combine this, then what it actually tells us, this pyrometallurgy, it basically deals with extraction of metals from their ores at elevated temperature or at high temperature. So we can say the pyrometallurgical route is nothing but it is basically extraction of metals, right, from their ores at elevated temperature, or I can say at high temperature. So we are actually giving very high temperature in order to extract the metal. So high temperature means what is the temperature range? It is basically 500 degrees Celsius to 2000 degrees Celsius. That is the temperature range which we actually give. And in the pyrometallurgical route. Now, these processes bring about physical and chemical transformations. So, this high temperature when we are actually giving, it basically brings about physical and chemical transformations. And what we achieve the separating the metal from the impurities. We can separate the metal from their impurities. That is the gangue materials, I can say. Okay, so this can be achieved and reducing the metal oxides to the metallic states. Here we will also see how we reduce the metal oxides. Reduce the metal oxides. So I can say MO, this is the metal oxide, to their metallic states. Right? Now, before we start talking about pyrometallurgy, we should understand that this pyrometallurgical route has some advantages. Why are we actually employing high temperature? What is the reason behind applying high temperature? So advantages of pyrometallurgy, if I basically talk about, there are many advantages as far as pyrometallurgy is concerned. So we'll be discussing the various processes of pyrometallurgy as well, like roasting, smelting. We'll be discussing all of them. But first and foremost, let us see what are the advantages of the pyrometallurgy. So what happens is, see, very simple. I can say that at high temperature, the reaction rate, any reaction you take. So if you are actually increasing the temperature, in most of the cases, our reaction rate is accelerated. So I can say that at high temperature, okay, when we are employing high temperature, right, the reaction rate is accelerated. The reaction rate is accelerated. That means the reaction rate becomes more at high temperature. So rapid reaction rate, and this is going to in turn give me increased production of the metal. This increases the production rate of the metal. Right? So this is my first benefit of giving high temperature. Now, at high temperature process, it permits the use of inexpensive reducing agents. We will see that. See, metal oxide, if we have the metal oxide, okay, and from the metal oxide, we are getting the metal. Say, for example, if I take an example, take this example, Fe2O3. So Fe2O3 is the iron oxide, I can say it is a hematite. Okay. Now from the hematite, what is the objective? The main objective of iron making. So this is the form we are getting in the nature, which is Fe2O3. We have to reduce it. Okay. We have to reduce it to iron. Okay. So now in order to reduce it in iron, what we do in the blast furnace? You see, blast furnace is nothing but it is a pyrometallurgical route only. So like that we should relate. Because what are we doing in the blast furnace? We are charging coke. Okay, we are adding coke. And what is the coke doing? The coke is actually the source of carbon, which is reducing my iron oxide. Okay, so in the iron making, I am actually creating a reducing environment. I can say that in the iron making, we are creating a reducing environment. And what is the temperature in the blast furnace? Obviously, it is very high temperature. So it becomes automatically. So because I am charging coke and I am burning the coke. Okay, so definitely we are adding fuel in it. So that means that high temperature is required for the process, right? So the same thing. Now we will see here. So we can say that high temperature process, the high temperature process, okay, it basically permits us to use inexpensive reducing agents. Very important from economics point of view. Permits us to use inexpensive reducing agents. Right? So we can use comparatively inexpensive reducing agents because the temperature is high. Okay. And another thing is, I can say that this is this can be a crude statement, but okay, we can say that almost the rate of every reaction doubles with 10-degree rise in the temperature. Approximately, I can say that the rate of all the reactions approximately doubles with just a rise of 10-degree rise in temperature. Okay. So pyrometallurgy, in the pyrometallurgy, we are actually having a very high temperature. So that means if I take a example, like if I take the example of this reaction, which is nothing but zinc oxide. Okay. Now the zinc oxide, I am reducing the zinc oxide in the presence of carbon. So this becomes a carbothermic reaction. Why carbothermic? Because high temperature, I am heating it. So very high temperature we are actually employing. So when zinc oxide is reduced with carbon, what it becomes? It becomes zinc plus CO. Okay. So this CO is in the gaseous form. So this reaction is going to drive more in the forward direction if my temperature is high, right? So that is the thing. And also, you see, there is another advantage. The physical separation of the product metal from the waste is facilitated. Because I tell you, okay, let us write it and then I will explain. The physical separation, the physical separation, okay, of a product metal, the physical separation of a product metal, okay, from the waste is facilitated. From the waste is facilitated. What it means? So it means that suppose I have a metal, so not a metal, suppose you have metal oxide. Now, say for example, you have, I can tell you, you can take the example of Fe2O3 only. Now, this Fe2O3 is basically, you know that it is reduced in stages. So Fe2O3 is first reduced to Fe3O4. This Fe3O4 is going to reduce to FeO, and FeO is going to reduce to Fe. Right? So I can take this FeO. So if I consider this FeO and we are giving it coke, okay, then what happens? Fe plus CO. Though this kind of reaction doesn't happen, we have seen that this is direct reduction reaction I am writing. So what happens is FeO comes in contact with CO, it becomes Fe plus CO2, and then the CO2 again comes in contact with the coke and it becomes CO. So if I complete this reaction, okay, this is a direct reduction reaction I have written. Direct reduction reaction. Okay, but what happens inside the blast furnaces? It can be broken down into two steps. Okay, I'm not telling it here. We have covered it in the iron making already. Now, the thing is, this FeO that is there, this is in the slag phase. Okay, and this carbon is the carbon that I have written here is the coke of the carbon. So I can say that this the slag, okay, it can come in contact with the coke, okay, and we can have the metal and the CO, okay, like that. So the point is that high temperature actually helps us to even to separate the metal from that of the slag. So you can say that the high temperature, the physical separation of the product metal from the waste is facilitated at high temperature. At high temperature. Okay. Right? So the liquid metal and liquid slag is basically separated out. The point is the liquid metal, so at high temperature, both the metal and the slag all are in the liquid phase. And if there is density difference, now the slag is less dense than that of the metal. Okay, then what is going to happen? The metal is going to sink in down. Okay, and the gang materials and the slag, actually slag is what I'll tell you, the liquid metal and the liquid slag separates up. So what I mean by slag? Slag is nothing but, I can say that slag is nothing but flux plus gang. Okay, we add the flux. So flux has a lot of, apart from taking up the gang, another what should I say? Another application of the flux is that the flux, okay, it is actually going to lower the melting point, of the gang materials as well, so that the gang materials, they can fuse, they can melt very easily. Okay, and once they can fuse or they can melt very easily, okay, what is going to happen is actually that it will mix and it will form the slag. Okay, so this is exactly what happens, right? So this is the main idea. Now, I can say that Another advantage of the pyrometallurgical route is that this is only the route, the pyrometallurgical route is the only route through which we can extract the highly reactive metals. So in order to extract the highly reactive metals, the pyrometallurgical routes and fused salt electrolysis, these are the two processes which we can actually use or employ in order to extract the highly reactive metals. So you can write only pyrometallurgical routes and fused salt electrolysis can be used, okay, to extract highly reactive metals. Say for example, what are the example? What I mean by highly reactive metals? Alkaline earth metals, right? Apart from that, I can write what? Zirconium and titanium. So we'll see basically extraction processes of zirconium as well as titanium. The extraction process of titanium is through the Crolles process, and zirconium is Van Arkel process. We'll see how we extract. Okay. Now let us first explain one of the pyrometallurgical route, okay, or a process. So it is calcination. What is calcination? First, what is calcination? Calcination is nothing but it is the thermal treatment of an ore. So you have a ore, thermal treatment means you have a ore and I am actually raising the temperature. That's it. I am just increasing the temperature of the ore, right? So thermal treatment of an ore, and it brings about decomposition. Why? Because the ore, see, all the ores are not that stable. Okay, there will be many ores. We will take example just now. If I increase the temperature, okay, what is going to happen is that this ore is going to break. Break means not physical breaking I'm talking about. It will decompose. Okay, and eliminates the volatile product. Say, for example, if you have any ore, okay, and if you raise the temperature, what is going to happen? See, the ores will obviously have some of the volatile products or volatile materials. Volatile material means which will directly they will get converted into the vapor phase, okay, at high temperature, and they'll go away from the ore. Like water vapor also. So water also you can say that actually what happens if I'm taking the example of aluminium, right? Al2O3 dot 2H2O. Aluminium is having dot 2H2O means that it is having the water, water vapor in it. Now, if I actually raise the temperature, what is going to happen is that this is going to this is going to get converted to Al2O3 plus 2H2O. So water is basically removed. So it has become dry now. Okay. So this kind of thing will happen, okay, at high temperature. So let us now talk about calcination. Okay. So calcination is nothing but it is the thermal treatment of an ore. You can write thermal treatment of an ore. It is the thermal treatment of an ore which brings about decomposition, and eliminates the volatile product So if there is volatile product, the volatile product will move out, will get eliminated. Okay. Say, for example, one very important example which you all must remember whenever we talk about calcination is it is calcium carbonate. So it is CaCO3. This is solid calcium carbonate. When I am heating it, okay, when we heat the calcium carbonate, it gets converted to calcium oxide plus carbon dioxide. Now, just think, what is the volatile product here? The carbon dioxide is the gaseous product, it is the volatile product. So, as you heat the calcium carbonate, it gets decomposed into two parts. One is the calcium oxide, another is the carbon dioxide. And as the carbon dioxide is a volatile product, it will move out. Okay, so you will always have the partial pressure of CO2 is going to drop. Okay, so that is going to drive your reaction more towards the right side. That means towards the product side. Okay. So now it has been seen that if I take the example of this reaction only, that is calcium carbonate, okay, solid, I am actually just heating it and we are getting calcium oxide plus carbon dioxide, CO2 gas. Okay. Now, what is the decomposition temperature? There will be some temperature which I can call the decomposition temperature at which basically this is going to decompose. That means the calcium carbonate is going to break. Okay. That temperature is nothing but 1123 Kelvin. So this is the decomposition temperature. At least I should give this temperature, because if I am not giving this, if the temperature is less than 1123 Kelvin, then the calcium carbonate will not break. Because you see, calcium carbonate, it has also some stability in it. Okay, so it will not break so easily. Okay, so that means we need to employ high temperature. Okay, so that has to be given. Now, there are, apart from calcium carbonate, there are other carbonates also. Okay, there are other carbonates also which get decomposed like this. Okay, so what are the other examples of the other carbonates that we can take? We can take the example of MgCO3, which is magnesium carbonate. Okay, and what is the temperature at which it decomposes is actually 417 degrees Celsius. Okay, 417 degrees Celsius. You can substantially find out how much Kelvin. 273 add karke you can find out that what Kelvin. Okay, so MgCO3 is going to decompose at 417 degrees Celsius. Then your MnCO3, manganese carbonate, this can also decompose at a temperature. What temperature? At 377 degrees Celsius. Okay. Similarly, your iron carbonate, FeCO3, this can also decompose at 400 degrees Celsius. Now you see the decomposition temperature are different for all these examples that we have taken, MgCO3, MnCO3, as well as FeCO3. We can see that clearly from this example that they are decomposing at different temperatures. Now then, can you just understand one thing, that if they are decomposing at different temperatures, I can actually apply differential calcination. Differential calcination. Okay. What is this differential calcination? That means if I am slowly increasing the temperature, suppose my temperature was 100 degrees Celsius. I have increased it to 200 degrees Celsius, 300 degrees Celsius, 350 degrees Celsius. Eventually, I have moved to 390 and 400 degrees Celsius. What will happen at 400 degrees Celsius? First, my manganese is going to decompose. MnCO3 will decompose first. And when it is going to decompose, it will become MnCO3 से क्या बनेगा? Okay, so it is going to become just like this. That is the MnO plus CO, right? So that is going to form just like this, CO2. Okay, so MnO plus CO2 will form when MnCO3 is going to decompose. Then at high temperature, when I am increasing the temperature at 400 degrees Celsius, what is going to happen? This calcium carbonate will decompose and followed by the magnesium carbonate. Okay, so depending upon which carbonate is more stable, the more stable your carbonate is, you actually need higher temperature in order to decompose it, right? Now we will see there are some steps which are uh, involved. Now, before our calcination, we do not just take the ore, okay, like that. Like if I'm talking about calcination, it is not like that, that straight away I'm going to take calcium carbonate and we are just going to heat it up. Okay, that is not the thing, how it happens. So step by step process is basically followed. What are the processes? Okay, step by step process is followed. First is basically our feed preparation. Feed preparation means that we would like to uh, uh, heat treat the material, right? So we will actually prepare the material before heating it. Okay, that is called the feed preparation. And the first step of feed preparation is what we discussed in our mineral dressing. What was it? It was nothing but comminution technique. So in the comminution, it comes under size reduction. So we need to reduce the size of the feed. Okay, by there are two methods of size reduction we already discussed, and these two methods are crushing and grinding. So these are the processes of the size reduction techniques. Crushing means when you are reducing the average size of a particle to about 6 millimeter. Okay, we will call it crushing. And when the size is reduced to further 6 millimeter, we call it grinding. Okay. Now, can you recollect that what are the, we discussed, what are the machines that are employed for crushing? Okay. And the machines that are basically employed for grinding. I am not going to tell this here. I expect you to write it in the comment. So please write it in the comment. What are the machines that we discussed for crushing and what are the machines that we discussed for grinding? Okay. So this was it. Now preheating. After the feed preparation, we should be going with preheating. We should be going with preheat. Preheating means once the sizing is done, now my ore is going to be preheated. I am going to heat the ore. Now, why this is done? Because the to remove the absorbed moisture, the ore will definitely contain some kind of moisture. So I have to remove. So to remove the absorbed moisture. Okay. So in order to remove the absorbed moisture, will be heated. And after that comes the, you see the calcination process, where I will just elevate the temperature, where physically adsorbed water is first removed. Okay, so the decomposition temperature, if I am heating it to the decomposition temperature, first physically adsorbed water is removed at high temperature, and then chemically bound water, hydrates and volatile compounds are also removed. So physically adsorbed moisture is basically removed by this preheating. Now, when I heat it to the decomposition temperature. When I'm heating it to decomposition temperature, what is happening? Now, what is happening when I'm heating it to decomposition temperature? You can say that bound water, chemically bound water, okay, and volatile compounds, right, like CO2 are evolved. Now, this is about calcination that we have discussed. Now I will talk about another pyrometallurgical process which is very important and we call it roasting. Okay, so we call it roasting. So what is roasting? Okay, so if we are asked that what is roasting? Okay, then what should be our answer? What is roasting? So you see, before I talk about roasting, I must say that there are certain ores, especially there are sulfide ores. If I talk about sulfide ores, means MS, metal sulfides. Say for example, I'm talking about PBS, lead sulfide. I'm talking about zinc sulfide. Okay, these are the sulfide ores. Uh, so they are heated in the presence of excess oxygen. So they must be heated in the presence of excess oxygen. So at high temperature, temperature is also high, and we are actually giving it oxygen. Okay. So what is going to happen? This sulfide ore is going to convert into oxide. So metal sulfide, say our main aim is to convert it from metal sulfides to oxides. Okay. So that is the main criteria, because from the oxide we can easily reduce it into the metal. It is very difficult, okay, to basically get the metal directly from the sulfides. So that will be better. That will be better. That what if we convert the sulfide to oxide, and then, okay, we do it. So this is our roasting. So you can basically talk about roasting. When I talk about roasting, you can basically write it here simply that uh, roasting means, I can say that sulfide ores, they are heated in the presence of heated in the presence of excess air or oxygen, okay, to convert them into oxides. Into oxides, okay, to convert them into oxides, or sometimes sulfates, or directly into metallic form. Okay, or directly into metallic form. So objective is to convert the sulfides into oxides. That is the main purpose. Now, and to the roasting, we also remove volatile impurities. Okay, so also volatile impurities are removed. So if there are any volatile impurities, that because I am heating it, so those volatile materials will also get removed. Right? Say for example, what are these volatile materials? It can be arsenic, it can be antimony, sulfur, and other oxides can also be considered. Now, the roasting, if I'm talking about the roasting, okay, we have different kinds of roasting. Okay, so say for example, first I should talk about oxidizing roasting. Oxidizing roasting. So if I'm talking about oxidizing roasting, what is oxidizing roasting? Okay, let us take an example. Sulfide ores. You have just sulfide ores. Okay. So sulfide ores, it is heated in the presence of excess air or oxygen. So you have the metal sulfide, you are heating it in the presence of oxygen, you are heating it. So it will simply get converted to metal oxide, okay, and you will get sulfur dioxide gas. This is an example of just an example of the sulfides. So oxygen is the, in oxidizing roasting, oxygen is the main reacting gas. Okay. And oxidation is the principal reaction. So I can say that oxygen is the main reacting gas and oxidation is the principal reaction. Is the main reaction. Because what has happened? The sulfide has converted to oxide. Okay. Let us take an example to understand it better. Uh, like the equation that I have written, only that equation I will write, like it is the metal sulfide. We are just giving it enough oxygen. So just one thing we need to keep in mind, that while we are actually uh, talking about the roasting, so you should be giving enough oxygen. It should be abundant of oxygen should be present. Then only your sulfide is going to get converted to oxide. Okay. And SO2, because SO2 is a gas, so you see that it will definitely come out of the system, right? It will come out of the system. So this is the thing that happens. Right? Okay. Now, okay. Now let us see. This was about the. Now we will see the step-by-step mechanism of oxidizing roasting. Okay. Let us understand it step by step. The mechanisms of oxidizing roasting. How it proceeds. See what happens. So we should be, while I am, see, feed preparation in the entire process, whatever process I am talking about, okay, you need to understand one thing, that feed preparation is something which is very, very important. Okay, feed preparation is very important. So feed preparation is important, and our ore particles, while we are roasting it or employing something for roasting. So our ore particle size of the ore particles should be less than 1 millimeter. It should be less than 1 millimeter. So that means your comminution is coming in the picture first. Before we start anything, we should reduce the size of the particles. Okay, because what happens is when your ore particles are small, you are reducing the size of the particles to the appropriate size. Okay, then what happens in the process? You are actually increasing the surface area. So when the size of the particles is reduced, the surface area is effectively the surface area is increased. So when you are increasing the surface area, what is going to happen? Your any reaction is going to be more faster, whether it is roasting, whether anything you talk about, because ultimately the more the surface area, more the reaction kinetics. Okay, so this is the basic. Now you see. So introduced in the, and after that you are going to put the ores in the roaster. Okay. And they are, okay, these ore particles, they are heated below the melting point. Typically about what is the temperature up to which we heat it. Okay, the temperature is basically 500 degrees Celsius to 900 degrees Celsius. This is the typical temperature range up to which we heat it. And at this stage, what happens? Sulfides become chemically reactive with oxygen. So we are just making the ground prepared. Okay, we are just making the ground prepared for the battle. So metal sulfide, just in open oxygen, see why roasting, why pyrometallurgical process is important, because see metal sulfides, if only oxygen could have reacted with metal sulfide and converted into metal oxide, then there would be no importance for the high temperature. Why are we giving high temperature? Oxygen is anyway present in the atmosphere. So metal sulfides are coming in direct contact with the oxygen also in the atmosphere. But that means that just oxygen is not enough. And along with the oxygen, we also need to prepare the ore. That means we need to reduce the size of the ore so that the ores are having a higher surface area and more higher surface area. That means now the oxygen are more susceptible to attacking the ores. Okay. And now the ores are prepared to convert it into from the metal sulfide to the metal oxide. Okay. So that is the main purpose you need to understand. Okay. Now, if I take the example, you take the example of a metal sulfide. So suppose this is the ore, one particle of metal sulfide. Now there is oxygen everywhere. So at high temperature, what this oxygen will do? These oxygens will directly come in contact with the metal sulfides, and first where the reaction is going to take place, obviously at the surface. The oxygen will diffuse at the surface, they'll react and they'll convert it into metal oxide. So from the metal sulfide, the surface now becomes metal oxide, MO. Okay. Now, eventually, my metal sulfide is going to shrink in size. This is something very similar to the shrinking model. I told we discussed it in the iron making class. The same thing happens in the shrinking model. Okay. And here we are seeing that how the metal sulfide, it basically reduces in size and it eventually gets concentrated at the core, and we are having more and more metal oxide. But you see one thing, this metal oxide layer must be porous. Why this metal oxide layer must be porous? Because if the metal oxide layer is not porous, porous means what? There should be enough pores. It should have enough pores, or it should have, I can say, it should have enough permeability. Permeability means that it should allow more oxygen to pass through this layer, because if it is not, if the metal oxide layer is not permeable, or if the metal oxide layer is not porous, then what is going to happen? Then ultimately what will happen is the oxygen will not be able to diffuse further and the reaction will stop, right? So you can say that the metal oxide layer should be more porous, should be porous and permeable, right? So this is the thing. So there is the growth of the oxide layer. And let us take an example. I take the example of, suppose, lead sulfide. So lead sulfide, we are actually giving oxygen, okay? And at high temperature, okay, what it is going to get converted to? It will get converted to lead oxide plus SO2. So this SO2 is evolving. Okay. There is also a auto reduction associated here. What is the auto reduction which is associated here? Like this lead sulfide will come in contact with the lead oxide. So I can say this lead sulfide is already present. Now lead oxide is also present. So they will just react with each other, okay, coming in contact with each other, and they will form, directly give this lead oxide, will reduce this lead sulfide, and we are going to get lead plus SO. This is called auto reduction. Okay, though it will be less in, obviously, compared to this, it will be auto reduction will be much less. Okay. Now, this is the oxidizing roasting. There is another roasting which we call volatilizing roasting. Volatilizing roasting. Volatilizing roasting. Now, what is volatilizing roasting? Volatilizing roasting means, what does it mean? You just think yourself. What can it mean? Volatilizing. That means there must be some volatile materials. Now we are roasting it. We are roasting it means we are converting the sulfides to oxides. Okay. So there must be some volatile oxides. Okay. So volatilizing roasting, the main purpose of the volatilizing roasting is it eliminates, I can say, it eliminates volatile oxides. And what are the volatile oxides? I can say As2O3. This is a volatile oxide. Sb2O3. This is a volatile oxide. And Zn. These are all my volatile oxides. So such oxides are basically eliminated. So the inflow of oxygen should be carefully controlled here because this volatilizing roasting is very critical. Why? Because if you are not controlling the inflow of oxygen and if you are providing more oxygen, then these can get converted, these volatile oxides, they will get converted to higher oxides, and higher oxides may not be volatile. So try and understand it. See, suppose when the metal, is oxidized to MO. Now suppose this is volatile. But when you further oxidize to MO2, maybe this is not volatile. But our idea is to eliminate this material M. So what should we do? We should control the oxygen supply absolutely according to the requirement so that the M gets converted to MO, but MO is not converted to MO2. That should be prevented. Now, if you are just giving uncontrolled oxygen, then M will eventually get converted to MO, and MO will also take up more oxygen and it will get converted to MO. Now, this MO2 is not a volatile oxide. Volatile oxide is MO. Okay. So that is the idea of the volatilizing roast. Okay. Now, after the volatilizing roasting, we should be talking about fluidizing roast. Fluidizing. Fluidizing roast. What is fluidizing roast? So these are all the examples of roasting I am talking about. Ore is heated in the presence of fluidizing agent. Fluidizing agent means the agent which will give you chlorine. Okay. To convert metallic compounds into their volatile chlorides. Sometimes some of the chlorides are volatile. So we need to convert the metallic compounds into their volatile chlorides. Say for example, if I have a metal compound, and I am actually giving chlorine in it, okay, in the presence of oxygen. So roasting means it will have oxygen. Always remember. So roasting without oxygen, roasting will not happen. So it will have oxygen. So we will get metal chloride. Okay, which is volatile in this case. Plus, okay, you will get the byproducts. Right? So this is the main funda. Now, objectives is to convert the metal oxides or sulfides into volatile chlorides, okay, and to separate the valuable metals from impurities, right? So these are the objectives. Now we talk about a very, very important thing which we call fluidized bed roasting. What is fluidized bed roasting? Okay, let us see. Fluidized bed roast. Please write. Okay. So what happens is, if I'm talking about roasting, we talked earlier also. So roasting is mainly employed, or roasting is mainly used for sulfide ores. So what we will do, we will finely powder the sulfide ores. Sulfide ores are powdered and they are suspended in a rising stream of hot air or oxygen. Maybe you will find difficulty. I will explain each and every sentence. So please don't bother about it. So first, let us see what we saw, what I told you, that finely powdered sulfide ores. So you have the sulfide ores, you have finely powdered it. Powdered means you have reduced its size. finely powdered sulfide ores. Now what you are doing, you are suspending it in a rising stream of hot air or oxygen. Suspended in a rising stream of hot air or oxygen. Or oxygen. What it means? It means suppose you have a bed like this, and this bed is porous. Porous bed. Porous bed means it has many pores. Okay, like this. Now on the top of this bed, the idea is you have these ores. Okay, they are just lying on the top of the bed. Finely grounded ores. So these are your ores, and these are finely grounded ores. And this bed is porous. So what will you do? Now you are actually blowing hot air or oxygen through these beds. You are passing hot air or oxygen through these beds. Eventually, what this hot air will do, or what this oxygen will do, this oxygen will obviously give an upthrust. This will give an upthrust on these particles, these finely grounded particles. It will give an upthrust to these particles, and finally these particles will rise above the bed. Okay, and they will, as if you will see that they are floating. Why you will see that as they are floating? Because of the upthrust given by the hot air. Now, what is the main, you see, what is the, if I say that advantage of this? Now, see, when these particles are suspended, they are in the suspended form like this, they are floating like this. Now, the oxygen will have a greater surface area to react with this. Oxygen will react in this side also, oxygen can react from this side also. So, they are all suspended in the air. Okay, and there will be greater or efficient, more efficient heat transfer also between the air and the particle. So all this will actually improve your, or I can say will basically fasten, or will actually accelerate the process of your roasting. That is the main idea, okay, of the fluidized bed roasting. So you can say particles behave when they are actually suspended, particles behave like boiling liquid. Like boiling liquid. Okay. Now, and this stage, when these particles are actually just floating, okay, that stage is basically called fluidization. Okay. Now, what is the principle of operation? So you have certain like stages of fluidization, rather I should say. So say for example, before fluidization starts, okay, before the fluidization starts, the particle will just be suspended on the top of the bed. Okay, particles are just suspended on the top of the bed. Once you start blowing the oxygen, okay, now what will this oxygen do? This oxygen will increase the pressure difference. The del P will, because this is at high pressure, but here there is less oxygen, so this is at low pressure. So once the more you blow the oxygen, initially the pressure difference will increase. So at the first stage, which is also sometimes called the fixed bed region, fixed bed region. Okay. At the fixed bed region, what happens? This is basically before fluidization has started. what happens is here particles are stationary. Your particles are stationary. Gas just percolates to the voids between them. Okay. Most importantly, what you should remember is your delta P or the pressure difference increases with the value of your gas speed U, where U is basically your gas speed. That means your oxygen speed or air speed, and del P is basically nothing but your pressure difference or pressure drop. I can say not drop, I should say here difference. Okay, that is the thing. Now, what happens? Eventually, as the velocity of the gas is increasing, so you are increasing eventually the velocity of the gas. So more and more del P will increase. Now, as the pressure difference is increasing more and more, eventually what is going to happen? Eventually, it will suspend the particles. The particles will get suspended in the air. Okay, and my roasting will be perfect. Okay. So the bed expands. You can say the bed expands. It looks like boiling liquid and excellent mixing. And this velocity is what we call minimum fluidized velocity. So where the fluidization takes place, the velocity of the gas, where the fluidization takes place is called minimum fluidized velocity. So you can write okay. So this is done. Now we have seen this. Now we will talk about sinter roast. The sinter roasting is nothing but it is also called the blast furnace or the blast roast. This is also called the blast roast. So what is the sinter roasting? What is sinter roasting? So in the sinter roasting, what happens? So this is a pyrometallurgical process. Fine sulfide ores, okay, are partially roasted. They are basically partially roasted and agglomerated into porous lumps or sinters by heating in the presence of air. So in sinter roasting, what happens is simultaneously the roasting process as well as the agglomeration process, okay, they go side by side. So I can say simultaneously the roasting process and the agglomeration process goes side by side. So this is very important. So let us take an example. Like if I am giving the example of lead sulfide. Lead sulfide in presence of oxygen. So this is a skeleton reaction only I'm writing, that I'm not balancing it. So it is becoming lead oxide plus sulfur dioxide. Okay. So this sulfur dioxide, it is going to, this entire process is basically exothermic. Okay. This is an exothermic reaction because this is the oxidation reaction. So this is exothermic. Now, what is happening is because it is exothermic high temperatures, so lead sulfide is being converted or oxidized to lead oxide. And at the same time, the heat evolved during oxidation. It causes the fine particles to soften and fuse together. So they are becoming agglomerated also. The heat evolved during oxidation. The heat evolved during oxidation. Okay. Causes the fine particles to soften and fuse together. Okay. So your agglomeration process is also taking place. That is the sinter roasting. Okay. So ultimately they form porous hard lumps, which we call sinter. So there are certain advantages of sinter roasting. What are the advantages? It converts fine sulfide ores into suitable porous lumps, which we can directly charge for smelting. Okay. So let us write the advantages. The advantages are converts fine sulfide ores into suitable porous lumps okay, for smelting. Right? This is one. And it utilizes the exothermic heat, which is energy efficient also. Okay. SiO2 we are getting, can be used for acid production. So these are all the advantages of, you see, the sinter roasting. Now, apart from that, after this, what we should talk about is smelting. So smelting is a very, very important pyrometallurgical process. Okay. So what is smelting? It is a pyrometallurgical process. Okay. A metal is extracted in molten form from its oxide or other compound by reducing it with some suitable reducing agent such as CO or H2, usually at high temperature. Okay. So what we get in smelting, you can directly say that uh, after roasting, we do the smelting. So roasted or calcined ore, if you take, okay, and if you add the reducing agent, like what are the reducing agent? You can use H2, you can use CO as the reducing agent, you can use carbon also as the reducing agent, anything according to the requirement. Plus, we will add the flux. But why will we add the flux? Because we want the gangue materials, the gangue, to basically get rid of the metal oxide or to get rid of the metal, and we want the gangue to be present in a separate phase, which we call the slag. Okay. So the flux, main purpose of the flux is that. So we will get in the product, we will get metal, okay, plus slag plus gaseous bipolars. Gaseous bipolars. So this is something which you will get here. Okay, if I'm talking about smelting. So the definition of the smelting is a pyrometallurgical process in which a metal is extracted in molten form. So you are extracting the metal in the molten form. So very important, the metal that you are getting in the product, okay, it is in the molten form from its oxide. So it is roasted, so it is metal oxide. So you have got it from the metal oxide or other compound. by heating it with a suitable reducing agent. So reducing agent we have given, and obviously this is pyrometallurgical route, so heat has to be there. And usually at high temperature, you are adding flux so that metal, slag, and gaseous byproducts you are getting. Okay. So let us basically see the objective of smelting. Or general some now let us look at some of the smelting operations. Okay. Okay. So say for example, if I'm taking the example of this Fe2O3, it will come in contact with CO, and so here CO is my reducing agent. Okay. And what we are getting? We are getting iron plus CO2. So this is one, right? Another is, I can say that CuO, copper oxide, coming in contact with a reducing agent like CO at high temperature. At high temperature, what is going to happen? Copper plus CO2. Okay. Similarly, PbO, lead oxide, at when it comes in contact with coke or with carbon, it will be lead plus CO2. Okay. So these are our examples. Okay. So what are the purpose of smelting? Why should we be doing smelting? So if I talk about the purpose of smelting, the main purpose of smelting. So what is the objective? Main purpose is to convert the metal oxide to convert. So first is basically metal sulfide from roasting. After roasting is getting converted to metal oxide. Now the metal oxide is to be smelted. So we'll convert the metal oxide into metal. Okay. So one objective you can write, we can write like this, that reduction. Reduction. That means reduce metal oxide or metal sulfide, whatever, to metallic form. Now, metal sulfide cannot be reduced directly to metallic form in most of the cases. So there is roasting. In roasting is involved. So you are getting, if you are getting metal sulfide, first you have to roast it. So by the roasting. So by the roasting, what you are doing, you are converting the metal sulfide into metal oxide. And after that, you will go for smelting. Okay. So roasting के बाद smelting होता है. Always remember. Then second is separation. Separation means separate metal from gangue. This is something very, very important for smelting. We are adding flux because of this only. So that the gangue goes into the slag phase and we get the metal. Then after that, we have the purification method. We have the purification method. And what is it? Remove unwanted elements. Purification means remove unwanted elements. Right? Formation of slag. Formation of slag. That means flux plus gangue is giving you the slag. Okay? Which removes impurities. which removes impurities, right? So these are some of the examples we can, and these are the purpose. Another smelting that I can talk about is our reduction smelting. Yeah. So reduction smelting is nothing but we are reducing it. Just that. Say for example, if you say that we are actually typically using reducing agents. Reducing agents are basically used. And what are the reducing agents that we use? We use carbon monoxide, as well as we use H2. Okay. Say for example, if we are using it, if we are doing like Fe2O3 in the presence of CO, okay, what is going to happen? You will get 2 times of Fe plus CO2. So this is our reduction smelt. So this is our reduction smelt, right? Similarly, PbO, lead oxide plus carbon, lead plus CO2. Okay. So this was all about the smelting that we saw, right? Now, in the smelting, we have seen that we have used flux. We have used flux. Now, what is the importance of flux? Okay, so I can say that importance, this is important to understand, importance of flux. So why flux is important, or why we use the flux? Okay, why do we use the flux? See, flux is important for slag formation. Is very important for slag formation. Now, why I say that flux is important for slag formation? Because when slag formation is taking place, how flux is actually helping in the formation of the slag? Flux combines chemically with gangue and forms fusible slag that separates from the metal. This is something very, very important. So flux, I can say flux combines chemically with gangue. Okay, and forms fusible slag. Fusible means at that operating temperature, the slag is liquid. Okay, fusible slag that separates from metal. So this is one very important example, very important criteria. As an example, I can say that suppose I am talking about CaO, calcium oxide. It is coming in contact with SiO2. So this is the flux. CaO is the flux. This is the gangue. So what this flux will do with the gangue, you see, it will form CaSiO3, which is nothing but this is the slag and this is calcium silicate. Okay. So it has taken the gangue and gone into the slag phase. Now purification of metal is also done by the flux. Like flux absorbs oxide, silica, and other non-metallic impurities, giving pure metal. So purification of metal, you can say. This is also done by the flux. Okay. Apart from that, temperature control, flux maintains the temperature. Flux lowers the temperature, the melting temperature of the gangue. Okay, so you can say flux lowers the melting temperature of the gangue. Okay, so smooth furnace operation, all these are basically maintained by the flux, which is important. Okay, now after this, we straight away go to the slag. Okay, we talk about the slag. Now let us talk about the slag. Now, when we talk about the slag, slag is what? It is a molten mixture of flux and gangue formed during smelting and refining operations, right? So this is a mixture of molten mixture of flux and flux and gangue, which is basically which is employed during the smelting operation. Now, so I can say flux plus gangue is nothing but our slag. This I can say, right? Now, acid slag, there are three kinds of slags we'll be talking about. One is acid slag. Now, the flux can also be acidic, basic, or neutral. Similarly, slags can also be acidic, basic, or neutral. If it is acidic slag or acid slag, it is more SiO2 or Al2O3 is there. Al2O3. Okay. So then I call it acid slag. Basic slag will basically contain Basic slag will mainly contain MgO or CaO. And neutral slag means it is a balanced slag. Neutral slag is a balanced slag. Okay. Now, what are the functions of the slag? Okay. What are the functions of the slag? It absorbs gangue impurities and make them fusible. So slag is going to take up the gangue material. So I can say it absorbs the gangue impurities and make them fusible. Apart from that, what it is doing, it prevents oxidation of the metal. The slag is also preventing oxidation of the metal, I must say, because slag is covering the melt. Okay, so the melt is not coming in direct contact with the oxygen. Like that, it is preventing the oxidation of the metal. And the slag is also preventing, if you think deeply, the slag is also preventing the uh, surface of the vessel where my reaction is taking place, because it is preventing the surface from getting corroded, right? So it forms a protective layer. Yeah, so this is important. Okay, and it removes sulfur and phosphorus. Okay. So now I can talk about the acid base character and basicity index of the slag. Okay, acid base character and basicity index of slag. Okay. So the basicity index of the slag is the ratio of basic oxides to the acidic oxides. So it is the ratio of basic oxides divided by, so I should not be writing ratio here. So it is basically summation of basic oxides divided by the acidic oxides. That means I can say it is CaO. These are all basic oxides plus MgO plus FeO plus Mn. These are basic oxides. And what are acidic oxides? Al2O3 plus SiO2 plus P2O5. These are the acidic oxides. Okay. So basic acid slag means if the basicity is less than 1, I will call it acidic slag. If the basicity is greater than 1, I will call it basic slag. Okay. So adjusting the basicity helps control the type of impurities removed. Okay. Now, this we have understood so far. Now, I should talk about a very important topic, which is nothing but structure of silicate slags. Structure of silicate slags. Now, if I talk about the structure of silicate slags, the structure of pure crystalline silica is how is the structure of pure crystalline silica? It is a 3D network consisting of silicon and oxygen atoms. Three-dimensional network consisting of silicon and oxygen atoms. So you see, silicate slag is going to be like silicon is there, and it is like tetrahedrally bonded to 4 oxygen atoms like this. So it is tetrahedrally bonded with 4 oxygen atoms. So I can say each silicon atom, okay, is tetrahedrally attached to 4 oxygen atoms, possessing both long range and short range order. There will be long range order and short range order. But in molten silica, what is happening? Because slag is nothing but it is in the molten form. So in molten silica, some of these silicon oxygen bonds are broken. Okay, some of these SiO bonds are broken. So you will not find long range order. Short range order is there. Short range order is there. Okay, but long range order is not there, I can say. Long range order is not. Okay. So this is long range order is lost in molten silica. Now the viscosity is very high in this case. Now let us see what happens. Now suppose we have a silicate structure. How is the silicate structure? This is the silicon. This is bonded with 3 oxygen atoms this side, and suppose 1 oxygen atom is in this side. So you see this is the structure. So this each silicon atom is tetrahedrally bonded with 4 oxygen atoms. So here there is 1 oxygen atom. Here there is 1 oxygen atom. Here there is 1 oxygen. Then it is bonded with this oxygen atom. This is again bonded with another silicon, which is bonded with again tetrahedrally bonded with 4 oxygen. Something like this. Now, when we are adding basic oxide, when we add basic metal oxide, when we add basic metal oxide into it, that is MO. Now what happens is the MO is going to dissociate into M2 plus O2 minus. Okay. Now this M2 plus ions, this is going to break the silicon oxygen bond. This bond is going to break and this bond is going to break. So it will be something like okay. So M2 plus. Got it? So it is breaking these bonds. And this is basically what you can say that this oxygen is having a negative sign, this oxygen having a negative charge. So this is just the force of attraction because of which that M2 plus is here. There is no direct bonding with the M2 plus ion and this oxide ions. But there is going to be electrostatic force of attraction between them. That is why they are there. Now this is when I am actually adding the basic metal oxide, this is so this kind of bond breaking is taking place. This lowers the viscosity of the slag. So that is why addition of the basic metal oxides, it lowers the viscosity of the slag because the bond is being broken. Okay, smaller units, because if the units are smaller, they are more mobile. They are more mobile means they can move freely more. So the viscosity is basically lowered. The breaking of silicate bonds, or you can say the silicate structure, lowers the viscosity. The viscosity of the slag. Okay. Now, I talk about classification of the slag. Classification of the slag. Now, when we talk about the classification of the slag, before I go into it, there is something we need to discuss, which is the silicate degree. This is moles of acidic. So silicate degree is what? Silicate degree, I can say that it is equal to moles of acidic oxygen from SiO2 divided by moles of basic oxygen from the basic oxides like CaO, MgO, and Fe. So you can see it is moles of acidic oxygen from SiO2 divided by moles of basic oxygen from CaO, MgO, and Fe. Like that. Okay. Now, basic slag means if the silicate degree is less than 1. So moles of acidic oxygen from SiO2 is less than the moles of basic oxygen. That means you have more basic oxygen. So basic slag is what? When the silicate degree, is less than 1. Okay. This is basic slag. So the principal anions, very important to understand this. Principal anions in the basic slag. What is the principal anions that you will find in basic slag? Principal anions in basic slag, that is going to be your O2 minus and SO4 4 minus. These are the principal anions in the basic slag. Okay. If I am talking about neutral slag, okay, then the principal anion is going to be, so in neutral slag, the silicate degree is going to be exactly equal to 1. And the principal anion is going to be, for the neutral slag, it is SiO4 4 minus. Okay. And for the acid slag, if I'm talking about the acid slag, okay, what is the principal anion? The silicate degree is greater than 1, and principal anions are going to be Si2O7 6 minus and Si3O10 8 minus. Okay, these are the principal anions. Right? Now, we go to another important part, which is called matte smelting. Okay, so let us see what is matte smelting. Okay, so let us see what is matte smelting. So what happens in matte smelting? In matte smelting, the extraction of metal from sulfide ores is basically taking place, but there is formation of liquids matte, and then this is converted to metal. That means I can write here the extraction of a metal, from a sulfide ore. And then what we are doing, production of a liquid matte. Production of a liquid matte. Production of a liquid matte from the ore. Right? And its subsequent conversion into metal. Okay. Now, the sulfide ore is fused with the flux first. Then what happens when the sulfide ore, we have a sulfide ore. Okay. So the sulfide ore, okay. So we have this sulfide ore. It is fused with flux. So we have added flux in the sulfide. So now what we will get? We will get molten mixture of sulfides. So matte is nothing but molten mixture of sulfides. This is matte. So ultimately you see what is happening. I have sulfide ores. Okay, I have sulfide ores. I am adding the sulfide ores with flux. And this flux is basically what this flux is doing. This flux is lowering the temperature, is lowering the fusion temperature or the melting temperature of the sulfide ores. So I am now getting a mixture of sulfides. Okay, and this is known as matte. Okay, so matte is metallic sulfides. So you can say that what is matte? And matte is nothing but metallic sulfide solution that contains minor amounts of oxygen and sometimes some metals too. So we can write matte is nothing but it is a metallic sulfide solution. Metallic sulfide solution. Matte is a metallic sulfide solution that contains minor amounts of oxygen minor amounts of oxygen and sometimes some metals. Okay. Let us take an example. Cu2s plus Fes. This is our matte. So this is a copper sulfide and iron sulfide. Okay. Right. Now, if I talk about matte, then we should talk about, now I should talk about one thing that this is one of the property you can say that a matte exhibits a high electrical conductivity compared to that of a metal. So you can write a matte exhibits high electrical conductivity compared to that of a metal. Okay, right. So you can see the electrical conductivity of uh, so okay, if I talk about the electrical conductivity, then metal possesses high electrical conductivity compared to that of a metal. So this is something like okay. So this is it. Now another thing is the density. If I'm talking about, then the density of the metal is going to be more compared to the density of the matte, and the density of the matte is going to be more compared to the density of the slag. So these are the densities, okay? So always, so metal will be at the, so there is going to be actually three distinct layers. You can understand. Metal at the bottom layer, you will find the metal, followed by the matte, and then on the top of the matte, you will find the slag. Okay, so this is the slag. Okay, this is the matte, and this is the metal. Okay, so exactly like this. Now, this was all about our matte smelt. Now we should talk about halide metallurgy and halogenation. And halogenation. So what it is? What is halide metallurgy and halogenation? Right. So let us now talk about halide metallurgy and halogen. Halide metallurgy means Uh, Basically, here what we are doing, this is a branch of metallurgy where halogen elements. What does halogen elements mean? That means chlorine, fluorine, bromine, iodine. These are our halogen elements. We are using halogen elements or their compounds, okay, to convert the metals or their compounds into volatile halides. So there are some of the halides which are basically volatile. We would like to convert them into volatile halides so that from them we can extract the metal easily. Okay. Say for example, I tell you one example. So just write down the definition, whatever we explained. Halide metallurgy. So what it means is that it is a branch of metallurgy. It is the branch of metallurgy where where halogen elements like Cl2, F2, Br2, okay, I2, these are all the halogen elements or their compounds. Sometimes we will also use their compounds like HCl, HF, NH4Cl, etc. Okay, they are used to convert metals or their compounds into volatile halides. Okay, into volatile halides. Say for example, you have a metal M and you are giving halogen here. X2 is the halogen. You are converting it into MXN, where X can be nothing but chlorine, fluorine, bromine, iodine, anything, right? So this is because why we have converted it into MXN, that is the MX, metal halide, because this is volatile. Okay, now let us see. Let us take an example and see. Titanium extraction process. Very important. So please note it down. Now this is also called titanium extraction process. This is also called Prall's process. So what we do in this process? What we do in this process? Just try and understand. The first step in this process is halogenation. That is chlorination. Chlorination. Okay. So we have titanium oxide, TiO2. we will just give chlorine to it. Okay. And in the presence of carbon, because we need to reduce it. Titanium oxide needs to be reduced. So carbon has to be given as the reducing agent. So your carbon is nothing but reducing agent. Okay. So when you are giving it in the presence of chlorine, it will get converted to TiCl4 plus CO. This CO is going to evolve. Okay. Because it is gaseous. Now TiCl4 is basically volatile. This is volatile. Okay. Now what we will do, so this TiCl4 in the second step, okay, we will take this TiCl4, titanium chloride, we will treat it with magnesium, Mg. Now, magnesium chloride is more stable compared to titanium chloride, or I can say that magnesium has got more affinity towards chlorine compared to titanium. So you will get titanium plus MgCl2. Okay. So this is absolutely the route which we actually use for titanium extraction. Okay. So this is the main thing. So TiO2, it contains oxygen. Carbon removes the oxygen and it gets converted into CO, and it helps in the formation of TiCl4. So this TiCl4 is a volatile liquid. This is a liquid, okay, and this is volatile liquid. And this can be purified by fractional distillation. And here we are reducing it. So TiCl4 is basically reduced by Mg, converted to titanium and MgCl. Why Mg? Because magnesium has got greater or stronger affinity for chlorine compared to titanium. From Ellingham logic, you can say that MgCl2 line is below the TiCl4 line. Okay, though Ellingham diagram, we basically use the metal oxides, but similarly for the metal chlorides, you can also draw the similar diagram. Okay, and you can say that obviously that MgCl2 line is going to be lower compared to TiCl4 line. Okay, now let us take another example, which is the formation of volatile iodide. Formation of volatile iodide. Okay. Let us see this. Formation of volatile iodide. Now, I will take the example of zirconium. Zirconium, when I give zirconium, we take zirconium in the presence of iodine. Okay, it forms ZrI4, zirconium iodide. Okay, now this zirconium iodide, when it basically is decomposed on hot tungsten filament, this is decomposed on hot tungsten. So very high temperature has to be given. That is the logic of using hot tungsten filament. Okay, so this at hot tungsten filament, when I am using this ZrI4, is basically get decomposed to zirconium plus iodine, I2, right? So this process, so by this process, this gives very pure zirconium. Okay, this gives very pure zirconium. So this zirconium that you are getting here is very, very pure. Because you see, I haven't used anything here, just pure decomposition. Okay, by in the hot tungsten filament. So this process overall, this is called, very important, please note it down. This is called the Van Arkel process. Van Arkel process. Zirconium extraction. So titanium extraction is Kroll's process, and this is our Van Arkel's process. Okay. Now we will see. So you see this halide metallurgy is so important. Now you will see magnesium extraction. Magnesium extraction. So this magnesium extraction process is what is called Pidgeon process. Right? So what we do in this process, we take MgO, magnesium oxide, in the presence of chlorine and carbon, so that we get MgCl2 plus Cu, carbon monoxide. So this MgCl, so why this is the reducing atmosphere? This carbon is actually providing the reducing atmosphere, and chlorine we are using so that we can convert the magnesium oxide into magnesium chloride, or we can reduce the magnesium oxide to magnesium chloride. Now, in the next step, the MgCl2 will be taken and it will be treated with sodium. It is the same mechanism basically, just like what we did for titanium. Titanium oxide we treated with chlorine and oxygen. Chlorine and carbon. So titanium oxide, because carbon was given, so it was reduced to titanium chloride. Okay, plus CO gas was produced. This titanium chloride we treated with magnesium Mg, because magnesium is having higher affinity. Now, when we are here, we are using magnesium. What should we use? Something which has got higher affinity towards chlorine compared to magnesium. So we will use here sodium. So it will basically form NaCl, 2 times of NaCl plus magnesium. So this magnesium is we are going to find this, get this magnesium. Okay. Right. So this was mainly our discussion about the pyrometallurgical routes. Okay. Now we move to a very, very important metallurgical route, which is nothing but hydrometallurgy. This is also something which we need to discuss, and it is very important also. Now, when I talk about hydrometallurgy, hydrometallurgy is nothing but it is the extraction of metals from ores or concentrates by using aqueous or water-based solutions. In hydrometallurgy, mostly we will be using aqueous or water-based solution. We will be using aqueous or water-based solutions, right? Right. So, see, hydrometallurgy treatment was generally confined to low-grade ores. And the stages involved in hydrometallurgy that we will write now. We will basically write down the stages that are involved in hydrometallurgy. So, stages, I can say, involved in hydrometallurgy. First is preparation of ore for leaching. Preparation of ore for leaching. Second is our leaching. So leaching operation, we will see what is leaching. Then separation of leach liquid. separation of leach liquid, recovery of metallic values from the leach liquid, leach liquid. And what else? Recycling of the leach liquid. Okay. So these are the stages I can see. Now, the first thing that we should understand is what is leaching. I have said this, leaching. Now, leaching means, if I'm talking about leaching means selective dissolution. So metallic values in an ore, they are selectively dissolved using suitable liquid reagent. So suppose I have a ore. This ore has many metals. Some of the metals I want to dissolve. Okay, selectively. I will put this ore simply in a reagent. Okay, this is not like that, but simply I'm making the situation simple in order to make you understand. Obviously, we will talk about all those stages, what we need to do with this ores. But suppose this ores has metal M, metal M is there, metal N is there, metal P is there, metal Q is there. These are all the metals. But I only want to extract the metal M from it. So I want the metal M to get dissolved in this leach liquid, okay, or in this reagent. Other metals will be N, P, Q. They will be in the ore only. I am not concerned about. I am only concerned about metal. Okay, so this is selective dissolution of the metal of our interest. I can say selective dissolution of the metal of our interest in the leach liquid. Okay, so please write the metallic values in an ore. The metallic values in an ore are selectively dissolved. They are selectively dissolved, okay, using suitable liquid reagent. Okay. Now, you see, first and foremost, before anything, uh, okay, first and foremost, before anything, what happens is I need to prepare the ore for leaching. So, preparation of the ore for leaching is very important. Preparation of ore for leaching. This is very important. Preparation of ore for leaching. Like this includes grinding, the physical concentration of the metallic values for the removal of the specific impurities and all this. Okay. So these are all important. Some sulfides are not soluble in the leach liquid. Okay. So sulfides, those sulfides which are not soluble in the leach liquid, okay, they has to be first roasted so that the sulfides are converted to oxides or sulfates, and then we will start the leaching, right? So preparation of ore for leaching is important, followed by the leaching itself. Okay, followed by the leaching, and after the leaching, uh, okay, we will do what basically separation of the leach liquid. Separation of the leach liquid means, see, after your leaching is done, so you have some residue left, and the leach liquid means whatever is there as the reagent. So you will separate the leach liquid, you will recover the metallic values because your metallic value is dissolved in the leach liquid. Okay, so your leach liquid is, in that sense, it is very rich, really, because it has the metal of your interest. Okay, and then recycling of the leach liquid. So that is exactly what leaching is. Now, okay, now the selective dissolution of the metal, as far as the leaching is concerned, it depends upon certain things. Okay, what are the things on which it depends upon? Okay, the selective dissolution is dependent upon certain things. Say, for example, let us take an example. I can write it. That is the leaching. I can say the rate of leaching. Selective dissolution means the rate of leaching is dependent on, okay, number one, temperature. Number two, pressure. Okay. Number three, volume of leaching liquid. Volume of leaching liquid. Pore particle size. Pore particle size. Okay. Pulp density, etc. These all. Okay. Now, let us take an example. I just gave you an example that sulfides will not be dissolved so easily. So if we have a metallic sulfide like zinc sulfide, what should we do? Before um, before going into the hydrometallurgy. So see, sometimes you have to take pyrometallurgical route before actually you start the hydrometallurgical process. Sometimes. So here is the example. What you will do here, we will simply roast it. So roasting, which is a pyrometallurgical route we discussed. Roasting will convert it into zinc oxide. Now you see zinc oxide, you can take it in sulfuric acid. You can leach it with sulfuric acid. This is called acid leaching. So H2SO4. When ZNO is taking in with H2SO4, it will get converted to ZnSO4 plus H2. Right? So this you have got zinc sulfate. Right? So you can say that ZnSO4 is dissolving Zn. There's a, sorry, H2SO4 is dissolving Zn. Right? Similarly, we have uh, examples like gold. This is called cyanide. It's gold cyanidation. If I take the example of gold cyanidation, if I take this example of gold cyanidation, what is it? You are basically using cyanides. Okay. So you have taken gold, okay, and we are giving it with cyanides. So cyanides, how you will give? Like NaCN. So I'm just writing cyanide here, Cn minus, that is the cyanide ion. Okay, in the presence of oxygen and water, H2O. So this Cn minus is coming from NaCN, sodium cyanide. Okay, this is come. So you will get basically a complex. You will get a complex of AuCN whole twice. Okay, so this is the gold cyanide. Okay, this is basically nothing but gold cyanide. So you have got the complex of gold cyanide and Right. So similarly, for this also, like for the silver also, you can use the cyanides. Okay. In the presence of oxygen and water, you will basically get silver cyanide. This complex you will, right? So this is called the cyanidation. This is cyanidation, right? So you see, rate now we will see, suppose, so this is the gold cyanide, this is silver. Silver cyanide. Okay. Now you see, rate of leaching depends upon the temperature, because as the temperature increases, faster kinetics, higher diffusion rate, and all this. Apart from that, it depends upon pressure, it depends upon the volume of the leach required, pore particle size, all these things. Okay, we talked about. Now, now I should basically talk about hydrometallurgy versus pyrometallurgy a little. Okay, so let us talk about this hydrometallurgy versus pyrometallurgy. So I can say that if I'm talking about hydrometallurgy, I can say that this is basically, what is the advantage? This is comparatively at low temperature, much lower temperature. Okay, but pyrometallurgy, I need to have very high temperature. This is one. Here we are using basically aqueous solution. Here we are using aqueous solution. Here basically we are using furnace, right? Then this is highly selective. So high selectivity. High selectivity. Here, this is fast and large scale. Large scale production is basically possible through pyrometallurgical routes. Hydrometallurgical routes is suitable for low grades. Suitable for low grades. And pyrometallurgical routes, these are suitable for high grades. Okay. So apart from that, there are also certain advantages as far as our hydrometallurgical routes are concerned. Okay. So what are those advantages? The advantages are, you can see, if I write about the advantages, ideally suited for, so advantages of hydrometallurgy. Okay. What are the advantages of hydrometallurgy? So it is ideally suited for leach and complex, lean and complex metals. So if the ore is also not that much good, then also I can use this route. Ideally suited for lean and complex metals. Number one. Number two, I can say create greater control at every processing step. So we have a greater control over the processing step. Okay. Then avoids environmental problems like high temperature, use of you see fuels, and apart from that, what is happening in roasting? In roasting, your SO2 gas is being produced, which is a very bad, because it causes a lot of environmental issues. Okay, so uh, that kind of thing is not basically uh, that kind of thing will not be done in case of our hydrometallurgical. So you can say it avoids environmental problems. It avoids environmental problems. Okay, like SO2 gas generation, which is common in case of roasting. Is common in case of roasting. And avoid reducing by coke, which is costly, which is a costly reducing agent. Okay. Uh, so these are some of the, I can say, the advantages, okay, of using the hydrometallurgical route. Apart from that, how are the recovery of metallic values, like from the leach liquor, how the metallic values are recovered? Recovery of metallic values from leach liquor. So there are various ways, like there is precipitation, there is cementation. Some of the processes we will discuss here. There is electrolysis, or electro-winning. There is ion exchange method, and solvent extraction method. Right? So let us take the precipitation. One example I can just give you. So if suitable reagent is added, metal forms insoluble compounds. When, okay, let us write here. So I can say that add reagent, suitable reagent. Now addition of suitable reagent, what happens? Metal forms insoluble compounds and it precipitates. So it is hydrometallurgical route. That means it is in the aqueous solution, and if the metal is forming insoluble compound, so definitely the metal is going to precipitate out. Say for example, you have AlOH4. Now, after addition of suitable reagent, it will get converted to AlOH3, and this is going to precipitate out, right? Okay, this is our precipitation method. Now we will discuss cementation. What is cementation? Okay. Now let us talk about the cementation. Now in the cementation, what is happening is, you see, cementation means a more reactive metal displaces a less reactive metal. More reactive metal, okay, it displaces a less reactive metal. So that means we can say that, say for example, you have Cu2 plus, okay, in the solution. So in the solution you have Cu2 plus, okay. Now if you just add iron, what is going to happen is that your copper is going to get cemented, okay. So copper is basically less reactive. So copper is going to be displaced from the solution. From the solution, iron, because iron is more reactive, iron is going to displace the copper from the solution. Copper is going to get cemented, okay, and you will get Fe2 plus aqueous. So I can say that in the cementation, there are two things which are involved. Okay. What are these two things that are involved in the cementation? One becomes the surface, one surface. Suppose this is the surface of the metal. So from the metal, there is going to be selective dissolution of, like, a part is going to be selectively dissolved. Okay. And there is going to be a part is going to be, so suppose this is, what should I say? Suppose if this is the metal surface, which is basically dipped in the solution, so it is entirely in the solution. So you see what is happening here. The copper is from the Cu2 plus, okay, it was in the aqueous initially. The Cu2 plus ions will come here, okay, it will take up the electrons and they are getting cemented as copper. So copper is getting cemented. On the other hand, what is coming into the solution? Okay, what is coming into the solution? Fe2 plus is coming into the solution. So I can say at one side, oxidation is taking place, and on one side, basically, reduction is taking place. So one side is anodic, another side is cathodic. Where reduction is taking place, it is cathodic. So this is my cathodic side, I can say, because here reduction is taking place because Cu2 plus is taking electrons and it is just placing itself in here. So this is the cathodic side, and this is the anodic side, where basically Fe2 plus, sorry, Fe iron is basically getting converted to Fe2 plus. Okay, and when the iron is getting converted to Fe2 plus, it is releasing electrons. The electrons is moving in the surface of the metal only. So there are many electrons, but the electrons will not go directly into the aqueous solution. The electrons will move within the surface. So you can understand from here that from that side, from where the metal is getting depleted, that is my anodic side, and that side where the metal is getting, what should I say? Where that side from where the metal is getting cemented, that is the cathodic side, because at that side my reduction is taking place. So that is why I can say that cementation is nothing but it is a combination of reduction and oxidation reaction, right? Similarly, in case of electrolysis, what happens if I'm talking about electrolysis or electro-winning? So this is basically metal ions reduced at cathode. Okay, metal ions are reduced at cathode. So you have Zn2 plus. It is basically taking up two electrons, say for example, getting converted into zinc. Okay. So this very pure metal is obtained basically. Now we talk about uh, a leaching process, which is called, we call it bacterial leaching. Okay. So we'll see bacterial leaching in a while. See, let us see the bacterial leaching. So when I am talking about the bacterial leaching, this is also sometimes called as the microbial leaching. Bacterial or microbial leaching. Right? What are the bacteria that are involved when I talk about this bacterial or microbial leaching? What are the bacteria that are involved? The bacteria that are involved are Thiobacillus thioxidans, okay, Thiobacillus thioxidans, Thiobacillus peroxidans, and Ferrobacillus peroxidans. Okay, these are involved in the bacterial leaching, right? So I can say in the bacterial leaching, what are the bacteria that are involved? I can say the bacteria that are involved are Thiobacillus thioxidans. These are the names of the bacteria. Thiobacillus thioxidans, Thiobacillus peroxidans, and Ferrobacillus peroxidans. Right? Now, what these bacteria do? These bacteria, they will oxidize metal sulfides into soluble metal sulfates. They oxidize the metal sulfides. Okay. So that is the MS, metal sulfides, into soluble metal sulfates. Okay. And they get energy from the process. So they are reducing it from sulfide to sulfate, and sorry, they are oxidizing it, and they get energy from the process. For oxidizing, they are getting energy. So the bacteria acts as biocatalysts. Okay. So I can write here. So this is basically my metal sulfide. Okay. In the presence of oxygen and water. So oxygen is also present in the atmosphere, water vapor or water is also present in the atmosphere. So basically for bacterial leaching, you do not require anything. Just if bacteria is present, it is going to act on the metal sulfide. So your metal sulfide is going to get converted to M2 plus SO4 2 minus ions. Okay, plus it will release H plus. So M2 plus and SO4 2 minus will combine to form MSO4, right? So from the sulfide, you are getting sulfate, right? So this is basically the idea of bacterial leaching, right? Let us take an example. Like say, for example, if I take copper sulfate, which is a chalcopyrite, CuFeS2, then we have in the presence of water and oxygen, and in the presence of bacteria, whatever bacteria we discussed, Ferrobacillus peroxidans, Ferrobacillus thioxidans, like that, whatever bacteria is there, you will get it Cu2 plus, okay, plus 4 times of SO4 2 minus, plus 2 times of Fe2 plus H plus. So this you will basically get. Okay. Now, what happens? This Fe2 plus is present. The Fe2 plus ions will basically further it may get further oxidized to Fe3 plus by the bacteria. Okay. So you have the MS Fe2 plus ion, sorry, Fe3 plus, if it is there, Fe3 plus ion. So Fe3 plus ion is going to give you M2 plus Fe2 plus elemental sulfur. So in the process, you see a lot of Fe3 plus ions is basically required in order to oxidize the metal sulfide. So if bacteria is not present, Fe3 plus ions concentration will gradually deplete. It will gradually lower down. Deplete means it will lower down. Okay. But because our bacteria is present, so consistently Fe2 plus ion, more and more Fe2 plus ion is being converted to Fe3 plus ion. So because of bacteria, okay, Fe2 plus ions will get converted to Fe3 plus ions, right? Because of the bacteria. So there is no dearth of or lack of Fe3 plus ions. So more Fe3 plus ions are basically present. So more conversion of M2 plus, I can say, right? And more conversion of M2 plus, and this thing is going to take place. Okay, right. Now, factors affecting bacterial leaching. There are certain factors which will affect the bacterial leaching overall. So we will have to see or talk about those factors now, that are the factors affecting bacterial leaching. So you see, bacterial leaching is what? Like I said, these are nothing but bacteria. So there is going to be effect of temperature. Very important, effect of temperature. Okay. So as far as bacterial leaching is concerned, direct effect on temperature, effect of temperature is going to be there, right? Now, because this bacteria will not survive at high temperature. Okay. So the optimum temperature level that you should maintain is basically 30 degrees Celsius to 35 degrees Celsius. That is the optimum temperature level. When the temperature is above 50 degrees Celsius, okay, the activity stops. Activity of the bacteria stops. So at very high temperature, the bacteria will not be active. Okay. And also, when the temperature is basically below 30 degrees Celsius, then also you see the activity also decreases. It will not stop eventually, but it will decrease. So rate of reaction will decrease, right? So, and when you go, if the temperature is basically above 70 degrees Celsius, the bacteria will die. Okay. Okay. Effect of nutrients, very important. These are bacteria. So they will have something to eat. So effect of nutrients. What are going to be the effect of nutrients on the bacterial? Okay. So these bacteria, the addition of bacterial nutrients will be beneficial. Like if you give them food, their food. Okay. So what are the bacterial nutrients? The bacterial nutrients are basically ferrous sulfate, FeSO4, FeS2, okay, then Fe2SO4, 3. These are the bacterial nutrients, right? So you need to understand this. Another is effect of particle size. Effect of particle size means pore size, particle size. So when I'm talking about the effect of particle size, what it means is that this bacteria concentrate at the solid surface that is in contact with the solution. Suppose this is the solid surface, but out of this surface, suppose only the lower part is in contact with the solution. So the bacteria will form the colonies only at the lower part, which is in contact with the solution. Okay, so that is the thing. So bacteria concentrate at the solid surface that is in contact with the solution and they build up colonies. Okay. We concentrate at the solid surface. At the solid surface. Okay. That is in contact with the solution. And it will build and it will build up colonies in those surfaces, right? So if the particles are finely grounded, means they are fine particles, then what happens? The surface area will increase. So more colonies for the bacteria. So bacterial colony will increase, I can see. But again, there has to be some limit also. If it is very finely grounded, then what is happened? The porosity will decrease. and air cannot reach. So your oxygen cannot reach that part. Okay, then automatically what happens if your oxygen cannot reach? Your oxidation is going to be hampered. Okay, it will going to slow down. And the bacteria also, see, they will also have a effect of radiation. Effect of radiation. Now, if these bacteria are exposed to direct sunlight, then the bacteria culture becomes inactive. When exposed to direct sunlight, so it has to be a bit shady, okay, not away from direct sunlight. So when exposed to direct sunlight, what happens? The bacterial culture becomes inactive. Okay? And there is also effect of acidity and aeration. And aeration. Aeration. So what it means? So there is a particular pH value where the activity of the bacteria is maximum. And that pH value is basically 2 to 3.5. Within this pH value, the activity of bacteria is maximum. Okay. So, and aeration means there has to be oxygen supply, constant, continuous oxygen supply. So oxygen supply should be essential for the bacterial survival, which is essential for bacterial survival. So this was all about our bacterial leaching. And with this, we have covered a big portion of our non-ferrous extractive metallurgy. I think that this lecture was helpful. This series was helpful to you. So all the best for your upcoming examination. And please subscribe to our MetaGate channel. And please comment also for if you have any demands or any questions. And please subscribe to our channel for more such useful updates and lecture series. Thank you.